Hi, welcome back. This is section 4.6. This is on modeling with exponential functions. So in this particular section, we're going to deal with some formulas and showing you some models, basically word problems, but using exponentials in order to do it. The first function, or the first one that we're going to do, is we're going to talk about exponential growth. And specifically, there's a formula out there for doubling. Now, what it means by doubling is in the problem it'll say that the population of this thing doubles every so many minutes or so. If that's the case, if you see anytime it says doubling, the formula you're going to use is n to the t equals no times 2 to the t divided by a. Now, n to the t stands for the population now. NO stands for the initial population. So whatever your population is at, if it says that you have 500,000 squirrels or something like that, but it started with 100,000 squirrels, the initial population would be 100,000. The population now would be 500,000. The 2 is the number 2. T is time. And A stands for the doubling time. And what they mean by that is that they will say for you, the population doubles every so many minutes or so many hours. Okay, it's very important that your T and your A need to be the same unit of measurement. Okay, so now on the next slide, I'm going to walk you through a problem. It's going to say, under ideal conditions, a certain bacteria population doubles every 3 hours. So it's telling you right now that it's a doubling formula, and it goes every 3 hours. So that is my A. Initially, there are 1,000 bacteria in the colony, so that is your NO. Part A will find a model for that thing. Well, finding a model is nothing more than you putting it into the equation. You don't know the population now. You know initially we were at 1,000 times 2. You don't know what the time is, but you know that the doubling takes 3 hours. Part B, how many bacteria are in the colony now after 15 hours? So what we're doing is we're going to take and put 15 in for T, and let's see what we get. So we take 1,000 times 2, 15 divided by 3. First of all, 15 divided by 3 is 5. Then 2 to the 5th is 32. And 32 times 1,000 is 32,000 bacteria in this problem, or in this case. Okay? So again, once you get that equation, once you get that formula, you're just going to plug in the numbers that you know or what you're looking for and see what you get. Then the last part will say how many hours will the bacteria reach 100,000, sorry. So this time we want to know, hey, my population's at 100,000. I started with 1,000. I know that it's doubling every 3 hours, but how many hours did it take to get that? So now here's where we got to work backwards. This is very, very similar to what we did in section 5, where you're going to divide first. If you're not sure how to divide that, whenever you got powers of 10 like that, they just cancel out zeros. So I have 100 equals 2 t divided by 3. And recall from the last section, when the bases aren't the same, you log both sides. When I do that, that allows me to put the exponent to the front. Then I divide both sides by the log of 2. People, just so that you guys know, the log of 100 divided by the log of 2 is not the same as the log of 50. So again, you can use your calculator to do all that work for you. So whatever the log of 100 is, divided by the log of 2 equals t divided by 3. In order to get rid of divide by 3, you times up both sides by 3. So in this context, this is the exact solution right here, but what's the exact solution for bacteria? And we don't know what that is. So we're going to type that in my calculator. Take 3 times log 100, close it, divided by log of 2, close it, and you get approximately 19.93 hours, because we're referring to hours in this case. So just so that you are aware of that, we're actually going to find out the times. These aren't going to be exact ones because you're dealing with bacteria, you're dealing with people, you're dealing with rabbits or squirrels or something like that, where you're actually dealing with physical things rather than more of a concept type thing. So that's the type for doubling. And by the way, the same concept is going to be kind of how they all are. It's just a different formula for each one. But that's the doubling formula one. The next one is also exponential growth, but this one's when it gives you a growth rate. For example, a lot of times you may hear a certain community is growing at a rate of 3.5% or something to that effect. This is the formula that they actually use to get that. So when you have people saying that your town is growing by so and so percent, this is the formula that they use. I remember it by Nort, because it looks like it sells out the word Nort, where NO and N to the T are the same thing. NO is initial population, or the starting population. R is your rate, and T is time. Okay, and again, they're going to do the same type of thing for you. Here's their example that they have for this one. Again, it says initial bacterium count in the culture is 500, so that's your initial population. A biologist later makes a sample count of bacteria in the culture and finds that a relative growth rate is 40% per hour. So 40%, anytime they give you a rate, they're talking about percentages. So we're going to put that into our formula. So according to that, we started with 500. E 0.4 was the growth rate, and we don't know T yet. That's my equation. That's what I'm going to use now to solve all the rest of the pieces. What's the estimated count after 10 hours? So again, I put 10 in for T, and let's see what we get. 0.4 times 10. I typically multiply that out first before I run it through my problem, just so that I don't screw that up. So that ends up being 500 times e to the fourth, which is approximately 27,300 whatevers. Okay, in this case, we're talking about bacteria. It could be people. It could be, anything for that matter. But then the other one is how much bacteria, or if it says that how much time passed to get to 80,000. Again, this is the exact same problem we did on the last one, or the exact same problem we did in section 5 even, where we're just trying to solve for T. So we divide both sides by 500 first. Get e to the 0.4 times T, which equals 160. Then we ln both sides. In this case, we're lnning because we have e involved. We logged both sides in the last one because we did not have e, we had a number. Okay, so that's kind of the difference there. So right now, remember the e and the ln cancel each other out. So the ln of 160 equals 0.4 T. Divide both sides by 0.4. And whatever that is my answer. It's approximately 12.7 hours. Okay, so this is how the growth rate works, whereas the doubling one was the previous one, where they're asking you to, depends on if it says doubling or whether it says growing at a percentage. Percentage is rate. Doubling is the first formula where it says times 2 to the sum. Okay. Then the next type of problem that they're going to talk about is the decay model. The decay model, MO, which I'm assuming you guys can figure that out right, what that is now, but just so you know, m to the t is how much you have now. MO is the initial, so what you started with. R is the rate, and t is time. The rate, though, however, is the ln of 2 divided by h. And what h is the half-life. Which means, a lot of times we use this formula when we carbon date things. Like, for instance, an archaeologist, when they want to figure out how long, when they find a fossil, how many years ago was this thing around? They will carbon date it. Carbon has a half-life of 5,730 years. So they figure out how much carbon is left, they work backwards, and they figure out this dinosaur or this woolly mammoth or whatever was roaming on our Earth this many millions of years ago. So that's how they do that when they figure that out. You know, Indiana Jones, for instance, just doesn't, you know, he knows it's this many years ago. There's usually more science behind it or lab work behind it than that. But just so you know, this is the formula that we use for this. Their example that they have, it says polonium-210 has a half-life of 140 days. So that's our half-life. Suppose the sample has a mass of 300 milligrams. So 300 is our starting point. So when we type this in and formulate an equation, we have 300 was our starting, minus. Now, sometimes you can write that as the ln of 2 divided by 140 and leave it like that. Or you can actually multiply that number out and you can go from there. A lot of times if you leave it that way, then you're going to be more accurate, because the ln of 2 divided by 140 is a number that doesn't stop. It just keeps going on forever. So you could multiply that out or figure that out. It's approximately, it'll be like negative 0.00495 if you rounded it, but again, that goes on forever. So if you leave it as the ln of 2 over 140, it will be more accurate for you. Then what they'll do from that is they'll say how much mass remains in 1 year. Okay, so for something like that, E negative ln of 2 over 140, and since I said 1 year, I'm not going to put 1 in there, I'm going to put 365. And the reason why I put 365 in that spot instead of 1 is because when they told me the half-life was 140 years, or days, I need to keep that in terms of days. I can't say it's not the same as the year or something like that. Those two units of measurement, when we talk about half-life and time, have to be in the same units. So for instance, when it said 140 days, that's why I had to put 365 there instead of 1. So when you type that all into your calculator, and again I would type it like this, 300 E, which automatically gives me caret, parentheses, negative sign, parentheses, ln of 2, which automatically close it, divided by 140, close it, time sign, 365, close it. It's a lot of parentheses, but what happens here is that you're taking the ln of 2 divided by 140 first, then you're timesing it by 365, then you're taking it to a negative power, and then putting that to the e. So it's kind of one of those things where be careful with how you type it in. If you chunk it, that might be a little bit easier, but if you're going to do it all in one step, that's how I would end up typing it in. And if I did all that, I'd have about 49.26. We'll say it was in milligrams remaining. Okay, so just so that you know, that's how it would be. If it says how long will it take for the mass to be 200, then again, what I'm going to do, I need another slide for this one though, is I put the 200 equal to the 300 e to the negative ln of 2 over 140, and then I'm trying to find t this time. So again, we're going to work backwards. You know, if you've been doing all the problems along with this so far from section 5 and this one, you're seeing the same problem. You know, there's not anything different here other than the numbers. The process is all the same. You ln both sides to get rid of e. So you got the ln of 2/3 equals negative the ln of 2 over 140 times t. In order to get rid of that, you divide. When you divide by a fraction, you're ending up multiplying by the reciprocal. So you have the ln of 2/3 times negative 140 over the ln of 2. When I type that in my calculator, I would type the ln of parentheses 2 divided by 3. It's not the ln of 2 over the ln of 3, it's the ln of 2/3. So that's very important that it's a little bit different there. Then a times sign, parentheses, negative 140. Oops, not close it. It's all right. Divided by ln, close it, equals t. And the reason why the double shot at the end of there is because I'm closing that out from in front of the negative 140. And I get approximately 81.9. And in this case, we're in days, because it said the half-life was in days. If it would have said the half-life was in years, I would have put 81.9 years. But again, this working backwards process is not anything different than anything we've done so far that we've done in the last 2 sections. But that's the decay problem. The half-lives, typically the books will give you a little chart that says what the half-lives are of certain ones. Like for instance, like I said, carbon-14 is 5,730 years. Some other known ones are in there. They're usually going to tell you what the half-life is in the problem. If they don't, they'll give you a chart that has it. So look for that. Or they might give you that in there. The last formula that this section has comes to us from Sir Isaac. He had a lot of laws, you know, like some of the big ones, gravity and whatnot, but his one that he came up with that we deal with in this is his law of cooling. What this is, or who uses something like this, there's a lot of people that use this, but a lot of times they have, like for instance on packaging for any type of food, where they ever tell you to let it cool for this many minutes, that's because this formula was found to have it cool so that you're not going to burn your mouth or something like that. So a lot of times when, like frozen pizza for instance, if you were to put a frozen pizza in, 9 times out of 10 we eat it way too fast, because all we do is we're so hungry that we just eat it and then we burn the roof of our mouth, and then 3 days later it's gone and then we forget all about it. But kind of the typical thing for that is, if you were actually to listen and adhere to the warning on the package, you should wait and you won't burn your mouth. So that's one of those things where that's where this formula is used. Another way that they use it is they use it in homicide investigations, where they figure out how long a body has been dead. They find a body, they can take the internal temperature and the temperature of the surroundings and figure out how long the body has been there for. So that's kind of one of those things where we have a lot of different purposes for it. But just so that you guys know what some of these are, TS is temperature of the surroundings. So for instance, you know, as I look at what the temperature is right now, okay, so if I'm looking at the temperature right now as I'm making this, it's 78 degrees. It's supposed to be 90 today, so the temperature of the surroundings would be whatever it is right now. So in this case, 78 would be what I would use for that. DO stands for difference in initial temperature and surroundings. Now difference, if you remember, difference means subtracting. So if the initial temperature of a frozen pizza, for instance, is 350 degrees, but in my house it's 75 or whatever it is, then I'd take that 350 minus the, or not the initial, that'd be the amount of the oven. Let's say the initial temperature of the pizza is like 225, and the temperature in my kitchen is 75, I would subtract those two to get that number. K is going to be a constant. They're going to give that number to you. They will tell you what that number is, so that way you don't have to find it. They typically will give that to you. And T is time. Okay. So, for example, for this one, you know, I kind of like those CSI shows and stuff like that. So, one of the problems says something like this. It says, Newton's law of cooling is used in homicide investigations to determine time of death. Normal body temperature is 98.6 degrees. Immediately following death, the body begins to cool. It has been determined experimentally that the constant in Newton's law of cooling is approximately 0.1947. Assuming the time is measured in hours, suppose the temperature of the surroundings is 60 degrees. So what I'm going to do is I'm going to put all the stuff that I know. So TS, for instance, they said was 60 degrees. Then what I would take is I would take for the DO, I would take 98.6 because that's our normal internal body temperature, minus 60 because that was the initial temp, or that was the temperature of the surroundings. E minus 0.1947 because that's what they told me that the K was. T. Now, one of the things that I almost forgot to mention is that negative sign that's up there with the exponent is very important. If you don't have that, you're not going to get it right. And that's the same thing with the growth or decay model. You got to make sure that those that negative is up there. If it's not there, your problem's off. Okay, so there's my equation. Then it says if the temperature was measured to be 72 degrees, how long has the body been dead? So 72 is the temperature now, plus 38.6 e to the negative 0.1947 t. So again, we're now going to figure out what t is. We're working backwards. It's been the same like this all the time. So I'm going to subtract 60, because again, remember, you get rid of adding and subtracting first, which gives me 12. 38.6 e to the negative 0.1947 t. Then I divide both sides. And again, I'm going to leave it as 12 over 38.6 because I think it's going to be more accurate my next step. I'm not actually going to divide that out. Then I ln both sides, which gets rid of my e. 38.6 equals negative 0.1947 t. Divide by negative 0.1947 to both sides. And whatever that is, when you type it in the calculator, I would type ln, it automatically parentheses. 12 divided by 38.6, close it. Divided by a negative sign 0.1947, and it's approximately 6 hours. So when you type that in, that's what I should get approximately for that. Should be about 6 hours. So for that particular process, it's very important. You know, I've messed up a couple times in myself, just not remembering the fact that that negative sign. Or another big one is not forgetting to subtract the initial with the surroundings in order to get that DO. That's been a problem. I think I've done that a couple times too, where I just forget that little subtraction step, and all of a sudden the whole number gets skewed. So be very careful, be methodical, and then you'll do just fine. Anyway, that's 4-6.